Have you ever ordered a pizza online? If so, you've already used network protocols without even realizing it. Let's break down this familiar process to understand how the internet works. When you type in the pizza place's website, you're using DNS. It's like a giant phone book that translates the restaurant's name into its internet address. As your order travels through the internet, IP acts as a traffic controller. It ensures your pizza request finds its way through the complex web of online connections. Once your order reaches the pizza place's computer, TCP double-checks that it arrived correctly. It's like the voice on the other end saying, "Got your order for a large pepperoni." If you're paying online, HTTPS keeps your credit card information safe. It's the digital equivalent of a secret handshake, ensuring only the pizza place can see your payment details. Finally, that live pizza tracker that shows your order's progress? That's using UDP to send you quick updates without waiting for responses. It's perfect for information that's useful now but not critical if occasionally missed. So the next time you're browsing the web or using an app, remember, you're essentially part of a giant, global pizza delivery system. Network protocols are the hardworking staff making sure your digital orders always arrive hot and fresh. Now, who's ready to learn more about how this all works? Today, we're going to take a deep dive into the world of network protocols. Here's what we'll be covering. We'll start with the basics. What are protocols and why do we need them? Then we'll explore the key protocols. HTTP/HTTPS for web browsing. DNS and IP for finding and routing data. TCP and UDP for data transmission. FTP/SFTP for file transfers. We'll also discuss email protocols like SMTP, POP3, and IMAP. Next, we'll touch on network management and security protocols. We'll finish with a review and connection session, and wrap up with the conclusion and importance of protocols. Let's dive in. Before we dive into the specific protocols, let's start by understanding what network protocols are, and why they're so crucial in our digital world. In simple terms, a network protocol is like a set of rules or guidelines that dictate how devices on a network communicate with each other. Think of it as a language that all devices understand. Just as people need to speak the same language to communicate effectively, computers and other devices need protocols to ensure they can exchange data smoothly and accurately. These protocols are the foundation of everything we do on the internet, from browsing the web to sending emails and streaming videos. Without them, the digital world would be chaotic and unreliable, and many of the services we rely on every day simply wouldn't work. Now let's begin our journey with HTTP, one of the most foundational protocols for accessing web pages. HTTP, or Hypertext Transfer Protocol, is one of the most well-known protocols because it's what allows you to access web pages on the internet. Whenever you type a website address into your browser, HTTP is at work. It's the protocol that fetches the web page from the server and displays it on your screen. Imagine HTTP as a waiter in a restaurant. You place your order, which is your request for a web page, and the waiter, HTTP, takes your order to the kitchen, the web server. The kitchen prepares your meal, the web page, and the waiter brings it back to you. Without HTTP, we wouldn't be able to browse the web as we do today. It's the fundamental protocol for data exchange on the web, making it one of the most important tools in our digital lives. Moving forward, let's take a closer look at HTTPS, the secure version of HTTP that adds an important layer of protection to your web browsing. HTTPS, or HTTP Secure, is like HTTP's more secure sibling. It does everything HTTP does but with an added layer of security. When you're browsing the web, especially when entering sensitive information like credit card numbers or passwords, you want to ensure that no one can intercept your data. That's where HTTPS comes in. It encrypts the data being exchanged between your browser and the web server, making it much harder for cybercriminals to steal your information. Imagine HTTP as a waiter, and now picture that waiter wearing a superhero cape. This is HTTPS. It's the same helpful waiter, but now they're protecting your data from cyber threats as it travels across the internet. This is why you see a little padlock icon in your browser's address bar when you visit a secure website. HTTPS is essential for keeping your online activities private and secure. Next, we'll explore DNS, the domain name system, which acts as the Internet's phone book, helping us connect to websites by translating domain names into IP addresses. DNS, or domain name system, is like the Internet's phone book. It takes a human-readable domain name, like www.example.com, and translates it into an IP address, which is the actual address where the website is hosted. Think of it this way. Instead of remembering the exact coordinates of your favorite restaurant, you just remember its name, and the GPS handles the rest. Similarly, DNS allows us to use easy-to-remember names instead of strings of numbers, like a series of digits separated by dots. Without DNS, we'd have to remember these numerical addresses for every single website we want to visit, which would be incredibly inconvenient. DNS plays a crucial role in making the Internet user-friendly, enabling us to navigate the web with ease. Speaking of IP addresses, let's dive into IP, the Internet Protocol, which ensures that data gets routed to the correct destination. IP, or Internet Protocol, is like the postal service of the Internet, making sure that data gets to the correct destination. Just like every house has a unique postal address, every device connected to the Internet has a unique IP address. IP's main job is to route data packets across the network, ensuring that they reach the correct destination. Imagine sending a letter through the mail. You write the address on the envelope, and the postal service makes sure it gets delivered to the right house. Similarly, IP assigns each device a unique address and ensures that data is mailed to the correct destination. There are two main types of IP addresses in use today. IPv4, which looks like a series of 4 groups separated by dots. Each group is a number between 0 and 255, and IPv6, which looks like a series of 8 groups separated by colons. Each group in IPv6 contains 4 characters, which can be either letters from A to F or digits. These addresses are essential for identifying devices and routing data across the Internet. Now that we understand how data is routed, let's learn about TCP, the protocol that guarantees your data is delivered reliably and in the correct order. TCP, or Transmission Control Protocol, is the careful package handler of the Internet. When you send data over the Internet, TCP breaks it down into smaller packets and numbers each one. These packets are then sent individually to their destination. When they arrive, TCP reassembles them in the correct order, checks for any errors, and requests retransmission if any packets are missing or damaged. Think of TCP as a meticulous package handler who ensures that every part of your shipment arrives safely and in the right order. If a piece is missing, TCP immediately asks for it to be resent. This makes TCP perfect for situations where accuracy is critical, like when you're downloading a file or sending an email. It ensures that everything you send arrives exactly as it should. While TCP focuses on reliability, UDP takes a different approach, prioritizing speed. Let's see how UDP works and where it's most useful. UDP, or User Datagram Protocol, is another method for sending data over the Internet, but it's quite different from TCP. While TCP is all about reliability, UDP is all about speed. UDP sends data packets quickly without checking if they arrive, or if they're in the correct order. Imagine a speedy courier who delivers messages as fast as possible without stopping to make sure everything is perfect. This approach is great for real-time applications where speed is more important than accuracy, like video streaming, online gaming, or live broadcasts. With UDP, you might lose a packet here or there, but the overall experience is smoother and faster. The trade-off with UDP is that while it's quicker than TCP, it doesn't guarantee that all the data will arrive intact or in the right sequence, making it ideal for applications where some loss is acceptable. Shifting gears, let's talk about FTP, the protocol that allows us to transfer files between computers over a network. FTP, or File Transfer Protocol, is the method we use to transfer files between computers over a network. Think of FTP as a moving company for your data. When you need to move a file from one computer to another, FTP steps in to help. First, you establish a connection to the remote computer, usually by logging in with a username and password. Once connected, you can upload, download, and manage files on that remote system. It's like hiring movers. You tell them what files to move and where to put them, and they handle all the heavy lifting. However, it's important to note that basic FTP isn't secure. It transfers your files without encryption, which means that anyone who intercepts the data could potentially see your files. For sensitive data, it's better to use a more secure protocol, like SFTP. Now, let's enhance the security of file transfers with SFTP, the Secure File Transfer Protocol. SFTP is like the armored truck version of FTP. It stands for Secure File Transfer Protocol, and it does the same job as FTP, moving files between computers, but with added security. SFTP uses encryption to protect the entire file transfer session, making sure that your data is secure while it's being transferred. Imagine you're moving valuable items, and instead of using a regular moving truck, you use an armored truck to ensure that everything is safe from theft or damage. SFTP often uses another protocol called SSH, Secure Shell, for authentication, adding an extra layer of protection. This makes SFTP the go-to choice for transferring sensitive files, or when security is a top priority. Whether you're dealing with personal data, financial records, or any other confidential information, SFTP ensures that your files stay safe during the transfer. Next, let's look at how our emails are sent across the internet with SMTP, the Simple Mail Transfer Protocol. SMTP, or Simple Mail Transfer Protocol, is like the mail truck of the internet. It's responsible for sending your emails from your computer to the recipient's server. Here's how it works. When you hit send on an email, your email client, like Outlook or Gmail, prepares the message and hands it off to the SMTP server. The SMTP server then finds the recipient's server and transfers the email over. It's like the mail truck picking up your letter and starting it on its journey. However, SMTP only handles the sending part, just like how the mail truck only picks up and drops off mail. When it comes to receiving email, other protocols like POP3 or IMAP take over. So, SMTP is essential for making sure your emails leave your outbox and get to where they need to go. Now that we've covered sending emails, let's see how they're retrieved from the server using POP3. POP3, or Post Office Protocol version 3, is like the mailman who delivers your emails directly to your device. When you use POP3, it connects to your email server, downloads all your new messages to your device, and typically deletes them from the server afterward. Imagine you're emptying your physical mailbox. You take all the mail out and bring it into your house. POP3 works well if you want to manage your emails offline, as all your messages are stored on your device. However, there's a downside. If you use multiple devices to check your email, it can get tricky. Since POP3 usually deletes the messages from the server after downloading them, the emails you download to one device might not be available on another. Despite this, POP3 is still a solid choice for people who prefer to have their emails stored locally. For those who prefer accessing their emails from multiple devices, IMAP is the protocol that keeps everything in sync. Let's dive into how it works. IMAP, or Internet Message Access Protocol, offers a different approach to managing your emails compared to POP3. With IMAP, your emails stay on the server, and you can access them from any device. Think of IMAP as a cloud storage service for your emails. When you connect to your email account with IMAP, it syncs the current state of your mailbox across all your devices. So if you read, delete, or move an email on one device, those changes are reflected everywhere. This makes IMAP ideal for people who check their email on multiple devices, like a smartphone, tablet, and computer. You always have access to your entire mailbox, and you don't have to worry about losing emails or having different messages on different devices. IMAP gives you the flexibility to manage your emails from anywhere, making it a great choice for busy, on-the-go users. Now let's talk about how devices automatically receive their IP addresses when they join a network, thanks to DHCP. DHCP, or Dynamic Host Configuration Protocol, is like a hotel receptionist for your network. When a new device joins the network, DHCP automatically assigns it an IP address, just like how a receptionist hands out room keys to guests. Here's how it works. When your device connects to the network, it sends a request asking for an IP address. The DHCP server receives this request and assigns an available IP address to your device, along with other network configuration information like the gateway and DNS servers. This process happens behind the scenes, making it easier for users to connect to the network without needing to configure their devices manually. DHCP simplifies network administration by preventing IP address conflicts and ensuring that each device gets a unique address. It's a critical service that keeps networks running smoothly, especially in environments with many devices like offices, schools, or large households. To keep networks running smoothly, administrators rely on SNMP. Let's see how this protocol helps manage and monitor network devices. SNMP, or Simple Network Management Protocol, is like the watchful eye of the network. It's a protocol that allows network administrators to monitor and manage network devices, such as routers, switches, servers, and even printers. SNMP collects data from these devices, giving administrators a clear view of what's happening on the network. Imagine you're a security guard watching over a large facility through a network of cameras. SNMP is like those cameras, constantly monitoring the network and alerting you if something goes wrong, like if a device is malfunctioning or if there's an unusual spike in traffic. Administrators can also use SNMP to remotely modify device settings, making it easier to manage large networks without needing to physically access each device. SNMP is essential for keeping networks healthy, secure, and running efficiently. When it comes to securely accessing a remote computer, SSH is the protocol of choice. Let's explore how it provides secure remote connections. SSH, or Secure Shell, is your secure private tunnel to another computer over the internet. It's a protocol that provides encrypted remote access to a computer, allowing you to control it as if you were sitting right in front of it. Here's how it works. When you connect to another computer using SSH, all the data exchanged between your computer and the remote computer is encrypted, ensuring that no one can eavesdrop on your activities. Imagine you're traveling through a secret underground tunnel that's invisible to everyone else. SSH is like that tunnel, protecting your connection from prying eyes. SSH is commonly used by system administrators to manage servers securely from a remote location. But it's not just for remote control. SSH can also be used to securely transfer files and even create secure tunnels for other protocols. It's an essential tool for anyone who needs to securely manage systems over the internet. Next, let's look at how network connectivity issues are diagnosed with ICMP, the protocol that's often behind tools like ping and traceroute. ICMP, or Internet Control Message Protocol, is like a sonar system for networks. It's used primarily for diagnosing network connectivity issues and testing whether devices on the network can communicate with each other. One of the most common tools that use ICMP is the ping command. When you ping a device, ICMP sends an echo request message to that device and waits for an echo reply. If the device responds, it means the network connection is working. If not, there might be an issue with the connection. Imagine a submarine sending out a sonar ping and listening for the echo to find out what's around it. ICMP works in a similar way for networks. ICMP is also used in the traceroute command, which helps map the path data takes to reach its destination. This makes ICMP invaluable for network administrators when troubleshooting connectivity problems. On a local network, ARP plays a crucial role in translating IP addresses to physical MAC addresses. Let's understand how this protocol works. ARP, or Address Resolution Protocol, is like the local guide that knows everyone's nicknames on a network. When a device wants to send data to another device on the same local network, it needs to know the other device's physical address, also known as the MAC address. However, devices typically communicate using IP addresses, which are like nicknames. ARP steps in to translate these IP addresses into MAC addresses, which are the actual real names used to identify devices on a local network. Here's how it works. If your device needs to send data to an IP address, it first sends an ARP request asking, "Who has this IP address?" The device with that IP address responds with its MAC address. This allows your device to send the data to the correct physical device on the network. Without ARP, devices on a local network wouldn't be able to find and communicate with each other, making ARP essential for local network communication. Now let's discuss RIP, one of the simpler routing protocols used to determine the best path for data across a network. RIP, or Routing Information Protocol, is like a group of hikers sharing information about the best trails. In a network, routers use RIP to exchange information about the routes they know, helping each other determine the best path for data to travel. Here's how it works. Each router maintains a routing table that lists the best known routes to different network destinations. These routers periodically share their routing tables with their neighbors, allowing the entire network to stay updated on the best paths. RIP uses a simple metric called hop count to measure the distance to a destination. Each hop represents one step along the path. However, RIP has a limitation. It can only count up to 15 hops, which makes it suitable for smaller networks but not ideal for larger, more complex networks. Despite its simplicity, RIP is easy to configure and works well for small to medium-sized networks. As networks grow larger, more sophisticated protocols like OSPF are needed to find the best routes. Let's see how OSPF calculates these paths. OSPF, or Open Shortest Path First, is like a GPS for data traveling within a network. It's a more advanced routing protocol used to find the best path for data to reach its destination, especially in large and complex networks. Here's how it works. OSPF routers exchange detailed information about the network's layout, known as the network topology. Each router then uses this information to build a map of the network and calculate the shortest path to each destination using an algorithm called Dijkstra's algorithm. Imagine using a GPS that not only shows you the shortest route, but also updates in real time based on traffic conditions. OSPF works similarly by quickly adapting to changes in the network, like when a router goes down or a new link is added. Because of its efficiency and scalability, OSPF is widely used in large enterprise networks where routing needs to be dynamic and responsive. Finally, let's explore BGP, the protocol that manages the flow of data between different networks and is critical to the functioning of the global internet. BGP, or Border Gateway Protocol, is like the air traffic control system of the internet. It's responsible for managing how data is routed between different networks, known as autonomous systems. BGP is crucial for the functioning of the global internet because it ensures that data can travel across various networks, finding the best possible path. Here's how it works. Each network or autonomous system has its own set of routes that it knows. BGP routers exchange routing information with each other, deciding the best paths based on factors like network policies, path length, and the number of hops. It's like air traffic controllers coordinating flights, ensuring that planes, our data, take the safest and most efficient routes to their destinations. BGP is often referred to as the glue of the internet because it holds the vast network of networks together, enabling global communication. Without BGP, the internet wouldn't function as a cohesive whole. Now that we've covered all these protocols, let's review how they work together in the activities we do every day. Let's take a moment to connect all the dots and see how these protocols work together in everyday scenarios. For instance, when you browse the web, a series of protocols come into play. DNS translates the website name into an IP address, IP and TCP handle the routing and reliable delivery of your data, and HTTP or HTTPS fetches the web page and displays it in your browser. Sending an email? SMTP takes care of sending your message, while POP3 or IMAP manages receiving it, depending on your setup. When you transfer files, FTP or SFTP gets the job done, with SFTP adding a layer of security. In network management, DHCP automatically assigns IP addresses, SNMP monitors network health, and SSH provides secure remote access. Finally, when it comes to routing data, RIP, OSPF, and BGP ensure that it reaches its destination efficiently, whether within a local network or across the globe. As we wrap up, it's clear that these protocols are the unsung heroes of the internet, working tirelessly behind the scenes to keep everything running smoothly. In conclusion, network protocols are the backbone of our digital world. They work tirelessly behind the scenes to ensure that everything from web browsing to email to file transfers happens seamlessly. Understanding these protocols not only helps you appreciate the complexity of network communications, but also equips you with the knowledge to troubleshoot issues and make informed decisions about security. As technology continues to evolve, so do these protocols, making it essential to stay curious and keep learning. The world of network protocols is vast and ever-changing, and by understanding these foundational elements, you're better prepared to navigate the digital landscape with confidence.